All right, okay, we're going to start back up. So it's my pleasure to introduce Joe Grabowski, who's going to give the next tutorial lecture. Joe is the project scientist on a mission called Maven, which is a Mars mission. But I think as Joe is going to explain to everyone, the science that Maven's doing is really close to the science we're used to thinking of at Earth for the CEDAR community. So this is, I hope this will be a really interesting talk for everyone. So.
Okay, I'm glad to be here. It's been a long time since I came to CEDAR. I've been involved with the ITM community a long time ago, and I got involved with Maven because of that. But Maven's been being sold as a planetary mission, and I'm trying to gear this talk more to some of your interests. It's not a tutorial. I'm going to give you snippets, bullets of some of the things we're finding out that hopefully you'll take something back from one of them or two of them. First of all, I want to give you some history. This is the best ionosphere-thermosphere-Magnetosphere mission I've ever been involved with. But my history goes back. The ones I've involved with never got flown on the Earth. So I'm happy to be involved. It was not selected because of ITM value. It's like in heliophysics, you have to have a focus. And if you're going to a planet for the first time and you don't know anything, it's a black box. And it's very difficult to propose to NASA's guidelines as to how you would focus on the science inside a black box. But in fact, back 10 years ago when we started this thing, we had the problem. Okay, we actually scoured the Deuteronomy from the proposal because some difficulties. And why it was selected, it found a focus. I'll get into that. But something is missing here. Yeah, this is what I did at CEDAR about 10 years ago. This, when we had missions like GEC, IT storm probes, and some Deep Dipper proposals, these were the comments we got from headquarters. Too complex, unfocused, incremental science, and a big one been studied for a century, and what is aeronomy was a bad thing, okay? And in fact, this picture in the back to show you, I don't want to say ignorance of headquarters, NASA headquarters, but we were told we're living with a star. They didn't understand the system. So I put this cartoon together. It's a one of a 4-sequence PowerPoint going tutorially through to explain to the people at headquarters what it was all about. And the conclusion 10 years ago, the IT community needs to get its act together. We were told this by NASA headquarters. Now, what's Mavens Focus? The sun goddess helped us. It blew away the atmosphere. The solar wind is blowing away the atmosphere, and this is the focus, where the atmosphere go. Maven's going to do all the ITM science you need, but the focus is where did the atmosphere and the water go? That's why Planetary funded it. Now, where the water went, I assume most of you are aware that there was water on Mars at one time. It's been advertised dramatically for a long period of time. Why the interest in Mars? Of course, you need water to have life. You have to have access to biogenetic elements and a source of energy. And these things are all there right now except the water. And the question, the compelling thing, did Mars ever have life? And how has the habitability of Mars changed over time? What really started, in my opinion, the Mars exploration program was this little thing. This is a rock that was knocked off of Mars and flew to Earth, and they looked at this and they thought this was a fossil of a microbe they found in Antarctica. I think that's since been disproved, but there was so much excitement at that time that the Mars Program Office was created about the same time to actually investigate all these missions we have in the future to look for life. And I want to emphasize, when we're looking for life at the present time, don't expect to have things crawling around or plants. We're just looking for microbes like this. It took multicellular microbes on Earth billions of years to develop. As you'll see, we didn't have that time on Mars. The water effects, well, you've flown in airplanes, you know, up on upper left, you know what rills look like, water coming off mountains, meanders. They have evidence of sedimentary layering. They're carbonate deposits in meteorites that you need water to do it. And Mars Express actually had, this is a statistical plot of escape from the planet. Mars is here, and you can see all these fluxes going back. They're seeing escaping ions from the atmosphere, and these are not just H+ ions, they're O2+, NO+, the whole atmosphere is being pulled out, the ionosphere is being pulled out. I don't want to leave you with the impression that there's no water at the present time. These are on the hills of Mars. The slopes are on this side, and these are sequences of satellites coming off. And you see these streaks. There's actually water flowing when sunlight is exposed on the side of these hills. Now, this is not oceans of water. It's not, we don't know what it's going to do for life, but this is actually, the reason it survives on a planet's surface is because it's probably like an antifreeze under the surface, a lot of saline solutions that let it come out when the surfaces are heated. The history we're talking about, this is an idea of what Mars evolved with. In the past, okay, a lot of eruptions, you had clouds back 3.89 billion years ago. There were pockets of water, and then the atmosphere disappeared, and now you have something, a desert-like environment, water just trapped in the polar caps or subsurface, which is not sufficient to actually cause the large body of water that we have evidence for. To compare Mars with Earth, I'll just show you. Okay, basically, Mars is half the size of Earth. And you have to keep in mind, its gravity is less than Earth, so it's easier for an atmosphere to escape from Mars than it is from Earth, so there's more escape going on Mars. Its atmosphere is predominantly CO2. It's about 1.5 times from the sun as Earth, so it's cooler in terms of the atmosphere. And in order to have liquid water, 2 conditions are needed. If they had liquid water in the past, they had to have a pressure like the Earth's atmosphere. At the present time, the pressure is 1/100th that of Earth. You only have 2 phases of water. You have solid ice, or it sublimates into vapor. It would not be in the liquid phase. To have water, as the evidence shows, billions of years ago, we need atmospheric pressure comparable to Earth and temperatures comparable to Earth also. It had to be a more humane environment. That's why they're thinking that life may have existed in the past, at least in a microbial form. Now, this is the conception now. About 3.8 billion years ago, the magnetic field disappeared from Mars. This is the conception now where the atmosphere went. There's an MHD modeling, and basically, you talk about the whole atmosphere going off, the solar wind is blowing it off. This is the concept we're coming up with. No one has come up with anything else. The water could not have gone down into the surface, and there's no evidence at all that there's anything under the surface comparable to that needed to produce oceans of water in the past. So we're starting off, first of all, this makes it a magnetosphere mission, and the fact that we are stripping off is the atmosphere makes it an aeronomy mission too, so it's all in your ballpark. One thing to keep in mind on Mars, okay, the main magnetic field disappeared because, well, Mars is a smaller body than the Earth. It may have had a dynamo, but small bodies actually cool off faster. It's like a shrew's eating all the time because it's radiating its heat, and an elephant doesn't have to eat as much proportionally to its volume. So Mars cooled faster, it lost its dipole field, but there are molten surface areas that retain some remnant magnetic fields. And this is a map done from MGS observation, magnetometer observation with Jack Carney and all, and it's the radial B fields. Remember, to keep in mind what happens next, it's in the southern hemisphere predominantly. The northern hemisphere is relatively free of magnetic fields. These are in the southern hemisphere, and these are opposite polarities. So we have dipole fields. You could call them mini magnetospheres, but not the type people are talking about in the moons. These are big enough to create a magnetosphere on Mars, where we get some physics comparable to what we're seeing on Earth's magnetosphere. The effects, just want to go through I'm not going to talk about the shock, since it's not, or the pickup ions, or the sheath out here, because this turned out to be a CEDAR presentation. But one of the things I will talk about with these dipolar fields, I'm sure you're aware, there's reconnection, which is a big point, and this plays a role in escape. I will be talking somewhat about that. And all the processes going on, pickup ions from the solar wind, there are roll processes because of these magnetic fields going on. And in a magnetosphere context, we have a plasma tail, just like on the Earth, a plasma sheet and lobes in the tail. So it's a magnetosphere mission. What Maven's interested in is the loss, where the atmosphere went. And what we've done, these are all the loss mechanisms that have been designed for Mars. And these are all derived from terrestrial science. So Maven and Mars atmospheric science is based on the Earth science, the same physics. But the same people are not coming over to Mars, they're staying on Earth. But we have things like the neutrals are in blue. You have Jeans escape going on. You have escaping neutrals, basically energetic particles from the sun, hit the atmosphere, knocks out the CO2. Photochemical escape. They're O2 plus ions. If the O2 plus ions recombine with electrons, the associative recombination gives you superthermal O atoms. So they will go out. Then we have the typical thing, aurora ion outflow from auroral regions like you have on Earth. What am I missing here? Well, the pickup ions and the solar wind interchanges with the corona species. They get picked up by the solar wind electric field and go out. So we are looking at all these processes. We have all the processes defined. No one has defined any alternative process how you could lose the atmosphere out. Now, the instruments we have, many of you are probably familiar with all of these. These are terrestrial-based instruments, but they're higher quality than some of the ones that have flown before. For the solar wind, solar storms, we have SWIA and SWIA. It's an energetic electron analyzer, ion analyzer. It goes from thermal energies, the electrons, up to about 20 keV. So we can look at thermal properties, photoelectrons. SEP, we go up to the MEVs, so we look at solar energetic particle properties. EUV looks at 3 bands from the sun, narrow bands, and it's using the FISM model to give us real-time spectra to fold into the ionosphere calculations and thermosphere calculations. The ion-related properties, we have Langmuir probe waves. These 2 standard Langmuir probes on long booms in the back to keep away from into the shadow of the spacecraft. And they also did a wave. It was like a sounder that really hasn't seen it. They're looking for Langmuir waves, and they're really detecting 2 magnetometers on the end of the solar rays, and static is one of the more valuable ones. It's Jim McFadden's solar terrestrial and thermal ion composition measurements. It actually goes from thermal, from 0.1 eV up to about 20 eV. It measures ionosphere flows, ion temperatures, and it goes out, it measures all the escape processes that we're seeing. Mavens Orbit, it was well planned. I'm just talking about the first year. Okay, we're into our second year, approaching a year and a half, but this was the pattern. We had an inclination that actually had us precessed. This is the latitude and essentially local time. So in 1 year, we precessed at all latitudes. We got a good sampling. And we're going back over this in a different sequence in the current year, and we put a proposal in for a senior review for 2 more years. So basically, we should have very complex coverage of entire space if we get renewed. Periapsis goes down to 150 kilometers. It approaches where the ionosphere is. Apoapsis is 6,000 kilometers. It's out in the solar wind. And this is a mapping of what the orbits look like during the 1 year. And we wanted to see the solar wind. The solar wind's one of the inputs. So we wanted to detect the solar wind and also what's happening in the ionosphere, so we have the cause and effect. We see observations in the sheath, the ion sheath, in the backside tail region going all back. We see all regions. One of the most important things we have in terms of altitude, since we're looking at particles that are coming from the neutral atmosphere, we have to go down as low as we can to see where they're coming from, and we have deep dip campaigns that take us down to 120 or 130 campaigns. We have 5-day deep dip campaigns. We did 5 of them so far going down, and you'll see some of the results in the presentations I'm having. But basically, we want to be below the exobase. For those not familiar with upper atmosphere, the exobase is once an ion gets up here, or a neutral gets up here, it's free. If it has enough thermal energy, it'll go away. There's no collisions to hold it back. The homopause is really the coupling between the well-mixed atmosphere like we have here at the present time. We're all species. The relative composition doesn't change as we go up to, say, a couple hundred kilometers or so. It's well mixed. We want to see that, but as you get up in the upper regions, you start getting mass separations, you get diffusions of chemistry. So you want to cover all regions to actually have a good mapping of what's happening from down on the surface all the way out into the solar wind where things are lost. We have a good path for following the escape. We had, I don't want to say we planned this, but we wanted to be on the declining phase of the solar cycle, and we're on the declining phase. We originally thought we'd be up on this phase, but because of delays in NASA funding, we're pushed for 2 years, so maybe it's just as well. But since we're looking at effects on the atmosphere, what controls it and what controls the escape, we want to make sure we're getting a lot of variations in the solar wind inputs, CMEs and The concept of going into the past is put together like this. In terms of time to the present day, the loss rate we expect to increase going into the past. We could, from our history of solar activity, we know from stars in the same sequence of our sun, we know what their solar winds are doing in the past. We know what their EUV is doing in the past. So we have a good concept of what the modeling of the inputs from the sun are going into the past. What we have to do at Maven is not just sample how the escape is changing with variations in the solar wind, EUV, but we want to use it to understand the physics of all the escape process. If we understand the physics, it's a simple thing of modifying the boundary conditions and going back in time to actually get a sequence to see how the atmosphere evolved in the past and how rapidly it disappeared. Now, these are a few of Maven's many discoveries. I tried to gear this for CEDAR and GEM. I took out some of the planetary one. One of the most exciting things were right after entry into orbit. If you've heard about Comet sighting spring, came very close to Mars, within 140,000 kilometers. And if you want to think of how close this is, if this comet came between the Earth and the Moon, it would come halfway between the Earth and the Moon. And you're talking about million-mile comas and everything. It would be a spectacular event. Needless to say, because of the dust and everything, we were scared, we were frightened in terms of safety. So what they did, all the Mars assets, Mars Express, Maven, they adjusted the period of the orbit so they're behind in the wake of the comet impact on the planet when the comet passed. And the comet, the tail passed, it was only a 1 hour encounter. We went through the tail in 1 hour. It's going fast. It's a high-speed comet, about 56 kilometers per second. So it just zipped back. The encounter was just one hour. The Maven IUV spectrometer saw it in Lyman Alpha, and you can see, and this is like a space telescope observation and stuff, but you can see the effect. And as I said, it would be a spectacular event that this came close to the Earth. People would be calling it the end of the world, or maybe it would be. Now, some of the effects we've seen, the cometary dust impacting Mars at high speed, of course, is vaporized and ionized. You saw the impacts, an earlier talk in this session, the impacts on spacecraft. Actually, the Langmuir probe that we have on here, they're in a mode. They actually saw impacts from the dust coming from the comet. In fact, they still keep seeing impacts during the course of time for dust coming in, micrometeors coming into Mars. The IUV spectrometer saw very bright emissions due to the metal ions, and they saw these things 120 to 150 kilometers. The nominal ablation altitude on Mars for the standard sporadic background is below 100 kilometers. So these are high speed. They're depositing material at high altitudes. NGIMS, the neutral gas ion mass spectrometer, we saw 11 different minor metal ion species and their isotopes. Actually verified that we saw these things. And we saw them, spacecraft was in an orbit about 185 degrees to above 300 kilometers. The metals have gone very high. In fact, this is an example of a pass, inbound and outbound, showing the enhancements coming down near periapsis of 4 species of the ions. And one of the things we're troubled with, we actually had detections, these metal ions up above 300 kilometers, which is very difficult to get them up there. They're not going to blade up there. It's still a question of what's happening. And these metal ion detections lasted for days. The IUV spectrometer, when they saw the effects, they saw it over a broad swath of the planet. It was a big layering effect. And looking at the magnetometer observations, Jared Espley actually came out with a paper. It also seemed like the H plus coming from the corona of the comet was like a CME, an intense CME hitting the planet. But one of the problems we had a CME hit the planet about a day or two beforehand. But he's convinced that we did see magnetosphere impacts and currents resulting from the comet. Now we go past the comet in terms of the metals, that there's interest here. This is just a snapshot of some of the things we're seeing. There is a consistent metal layer. It's always there. It's like on Earth. There are metal ion layers on Mars all the time. Previously, Mars Express had radio occultations, and they saw sporadic layers at very low altitudes below 100 kilometers. They interpreted this. It couldn't be anything else but metal layers. But they were measuring electron densities. And radio occultation only has a threshold of a couple thousand per cc, so they're only seeing the big events. With NGIM's observation, this is one of our deep dip campaigns, and I'm saying, that's why it's really first of all, the IUV spectrometer consistently detects magnesium Fe+ on every orbit when they have a limb scan, so it's always there. And this is the profile they have, and this is one of John Plain's model of the magnesium plus. They never really go below the peak of the layer because of atmospheric scattering effects. They can't really see it. But the source of the metal ions is down below. You ablate the metals from the meteor, the neutrals charge exchange with the ionospheric O2+, and then you get the metal ions. And if they appear at higher altitudes, the current conception is they diffuse upwards. NGIMS on one of the deep dip profiles. This is kind of exciting for meteor people because these are the types of profiles we see on an inbound leg of one orbit, okay? You can see the major ions, Fe+, magnesium+, and sodium+. These are the same types of concentrations we see on Earth. The relative composition is still dependent upon the chemistry. But one thing I've shown on this, I've drawn a line on this exponential plot. The vertical profile is characterized by a constant scale height. And when we looked at the CO2, the major atmospheric species, on the same thing, the CO2 has the same profile. So these species are tracking the neutral atmosphere. This is something that doesn't occur at Earth. On the bottom, you see a profile in the southern hemisphere. Remember, we have magnetic fields in the southern hemisphere, and these are the typical structures. This is more in line of what we see at the Earth, where you have magnetic fields. You have wind shears, you have currents across magnetic fields, you have, convergences and divergences of the field through the shears. In the northern hemisphere, where this was taken, actually all these models for the terrestrial, one-dimensional models of the terrestrial meteor ionization, they really don't fit the terrestrial observations because of structures like this, but they work on Mars. We have one-dimensional profiles. We don't quite understand the waves on this. Conjecture is they're probably gravity waves and the ionosphere actually affecting it, but we're talking about periods about, these altitude profiles about 1-2 kilometer separation. I'm not quite sure we have those type of scales in the gravity waves. Something of interest yet still going on. Now we start getting into topology, which we don't have before. This is an example of the measurements from the neutral ion spectrometer, the neutral measurements. CO2 is the dominant species. Oxygen is the second dominant species. In fact, oxygen is very important because it's a reactive species for a lot of the chemistry and escape processes going on. So it's very important to know how the oxygen is varying with altitude. The CO2 is rather stable, except in times. This is actually the relative percentage of the variation. So I want to make, but this is gravity wave structure, amplitudes about 0.5 of the points. And one of the things about Mars is, well, you know, on Earth, gravity waves are very important. They dump a lot of energy from low altitudes up above. But you have to remember, Mars is a smaller planet, it has lower gravity. Its topography is much more, I don't want to say violent than Earth, but it has a mountain that's bigger than any mountain on Earth. So we have a situation creating gravity waves, and we're getting a lot of gravity wave structures at the terminator of the planet. We go from day to night. It's like the flow of the neutral atmosphere from day into night becomes unstable and starts causing turbulence. This was seen on Pioneer Venus, the same type of thing. So it's a very structured gravity wave medium, and we still haven't looked at how much energy it dumps into the thermosphere and what it's doing yet. These are first observations. We haven't done the modeling for it. And to put these in perspective, these are, okay, this is the CO2 variation statistics for the first year as a function of solar zenith angle. You can see it dropping off and it becomes cooler. We measure temperatures by the scale height of the CO2. So we have temperature measurements, neutral temperature measurements, which are valuable. And to put this, 2 days ago, I think it was the 40th anniversary of the Viking. And to put into perspective what we have now, the Viking had 2 landers with Bill Hansen's RPA on to look at the atmosphere, and 2 landers in the same location on the day side. And right now, in 1 year, we filled in the gap, and we're still filling it in. And I want to make the point, very large wave structures at the terminators. Besides the lower atmosphere, there was a session yesterday on the effects of the hydrogen corona on the inner plasmasphere that I was into, and it's kind of interesting. These are coronal images of IUVS, and these are atomic carbon, atomic oxygen, atomic hydrogen. And these, basically, as I said, they're above the exobase, so we're seeing particles that are escaping. We're still trying to analyze this. The atomic hydrogen, detailed observations done on this. All we had for models, and maybe it's like this on Earth, for the corona of these species is a spherically symmetric distribution, genes type distributions of these things. And we're not seeing that. When we compare the hydrogen corona, for example, to one of the models, the steady states, spherically symmetrical, we get large deviations. It's nothing like a steady state. In fact, we're getting changes in the hydrogen distributions at high altitudes on the order of seasons, or maybe even less. And it's kind of a puzzle. How the heck does the hydrogen get all the way up from the surface of the planet through the collision-dominated regions out into these corona regions? It's a big problem. When we look at ions, okay, Viking had 2 profiles, and I guess they had maybe 3 ion species going down 2 locations. This is one orbit from NGIMS, the ion mass spectrometer, neutral spectrometer, and these are the species you're seeing. I don't forget. O2 plus is the major species in the ionosphere on Mars. It's like the ionosphere on Mars, the ionospheric layer is an E region like Earth. It's very comparable. It's a photochemical E layer on the day side. But all these other species, if the spectrometers we flew on Earth, I think they measured at most 8 species. Imagine how much fun it would be if you've got this type of profile on Earth, what the chemist would do. And one of the interesting features we're finding out, we never thought water would exist at high altitudes on Mars. Okay, it's at the surface. We thought, like on Earth, the mesopause would be a cold trap, it wouldn't get up. But if you look at this profile, we're getting OH components, H2O plus, all components related to the carbon, oxygen, water-containing ions. And if you look, we're talking about altitudes of 400 kilometers. We're going up above. Jane Fox did a thorough study. There are 2 alternatives for this. You could produce them in situ just because of the ordinary oxygen-hydrogen distributions. She said the chemistry didn't support that. The other one was maybe you have meteoroids coming in and you have a water component, but why you would dump it up here at these altitudes is not known. So it's still somewhat of an open question, but it's evidence that water is coming up from the surface all the way into the ionosphere that's affecting things. Another surprising result. Oh, and I just plot, this is an orbit on the side. We saw the waves and the neutral gases. This is one orbit coming inbound and then outbound again. Here's the altitude plot. And again, you look at the O2 plus, the CO2 plus, we're seeing waves on here. It's a very dynamically wavy ionosphere in addition to atmosphere. Expanding on the composition or global scale, on the left, I'm looking at O2 plus and O plus, the major ions. You'll see O2 plus, the red, is actually dominating at low altitudes, and O plus becomes more important as you go up in altitudes, but O2 plus is still dominant. You gotta be careful, these scales are different. But again, this is one of these water tracer ions, and if you look at it, we're getting significant dawn-dusk behavior. We don't know if it's coming from water from the surface, why you have a profile like this at the terminator, nothing in the day side. But the dawn-dusk asymmetry in the O plus, you can see on top, basically extends further into the night than on the dawn and dusk side. And this is another feature. On Earth, if you deal with the E region on Earth, the dawn and dusk E region peaks going into the night side, you go through the terminator from day into night or night into day, the profiles look essentially the same. On Earth, the reason they're the same, the ionosphere rotation doesn't have an effect. On Earth, there are ionization sources at low altitudes at night. You have scattered sunlight, an ionization source, and you have starlight coming in that actually produces ionization on night. So you have an ionization source at nighttime that makes the Eregion symmetrical between dawn and dusk at the terminators. These are Langmuir probe observations of a sequence, electron density at dawn and starting at dusk, and local time scale. But the dark blue is at dawn. You go into nighttime, it's the lighter regions, and the dusk becomes the lighter red. And in particular, the ion temperature measured first time. We have drastic changes in the ion temperature. At dawn and dusk, they're comparable near the terminators, but as you go into the night, you start getting a lot of heating, except at low altitudes where you're actually cooling to the neutrals. Extremely interesting changes in temperatures that depend upon local time. Now, one of the things I want to, okay, I guess I did have bullets to this up here. Yeah, this is something I've been working on. There's a typical conception about Mars. Like on Earth, you know, the atmosphere rotates the planet, even when you get up in the thermosphere. Like now, right now, you're moving about 450 meters per second down here. You're moving pretty fast. But you don't feel it, but it has an impact on how you generate the motion at high altitudes. This neutral wind, when it crosses the magnetic field, creates a dynamo on Earth that creates an electric field, couples up to the magnetic field, and the ionosphere essentially co-rotates with the magnetic field on the Earth because of the high speed here. The solar wind-driven tide waves on Earth are only of the order of 200 meters per second or so, compared to 450 meters per second of this great wind we have in inertial space of the wind. Mars has a smaller planet. Its surface velocity is only of the order of 200 meters per second. The winds on Mars, these are from Mars general circulation ITM models. On the top, you have wind vectors showing latitude, and this is basically solar local time on the side. If you look at the vectors on these things, you're talking about 250 meters per second. And these are the winds with respect to the planet. To actually find out in inertial space, you have to add the planetary rotation or subtract the 250 meters per second to this. And if you do this, at dawn, going from night into day, you may not be moving from night into day. The neutral wind is taking you still into nighttime. Whereas at dusk, you may have more enhanced rotations from day into night because of the winds carrying into nighttime. This concept of the ionosphere rotating with Mars and the atmosphere is dubious at best at the present time. I also want to show this. In fact, Maven has developed in our senior review proposal, we have two things that we're developing for Maven that will be interesting to people. First of all, we have the NGIMS has the capability of measuring neutral and ion winds. And the way it does that, the ion spectrometer is a very narrow field of view, and it's on a platform below the spacecraft that can rotate, so it can actually look at the distribution, and we're folding it in. And this was a test case of 3 orbits of neutral measurements from NGIMS. And we plan to have a cadence of these things. We're going to measure them continuously from now on. They also can measure ion measurements. So we envision if we go for 3 years, we're going to have a database in the ionosphere of ion vectors and neutral wind vectors that surpasses anything we have at Earth. In fact, I'm a great advocate. You have to take Maven and fly it to Earth, but that'll never fly. It's not focused enough. The Nightside Ionosphere, besides dawn and dusk, another difference on this, as I said, on the Earth you have sources. We don't have anything like an Eregion like on Earth because it's dominated by photochemistry. Oxygen never gets produced, so it's competitive with the fusion like it is on Earth to give you an Eregion. So we just have this chemistry region. And the question is, if you cut off photoionization, and there are no ionization sources at night, where's the ionization coming from? There are 2 of them. This is an example from Venus where we had observations. The Venus, you look at it this way. On the day side, without magnetic fields, if you have a source of plasma on the day side, you're producing ionization on the day side, and nighttime, it's a photochemical sink. So intuitively, obviously, you're going to go from day to night. The flow is going to go from day to night. You have flows going from day to night. On Venus, it happens, these things actually go supersonically, but if you go in the nighttime, actually come down, it maintains the ionosphere for a period of time. The other possibility is it goes back to these magnetic fields. There are many magnetospheres, but they have terrestrial-like consequences. If you have a magnetic field and you have ion flows coming from outside, it's a barrier to the ion flows. The ions cannot get inside it. So we'd expect maybe density differentials between inside and outside. Secondly, you have no ion sources inside. If you have an ion source, a precipitating ion source, it's going to happen in the cusp regions where the field lines open up and go out into the tail. And this is where we see energetic particle precipitation going on between the dipole fields. But so inside these magnetic field regions, we should expect a totally different population than outside. The production is outside, and it's impeded inside. On a recent study, this is what we found. This is a band of altitudes. I think it's 150 to 170 kilometer altitudes. The zenith angle is greater than 120 degrees, and we've looked at all the O2 plus densities as a function of longitude. And remember I pointed out the magnetic fields are in a certain longitude range, and this is the average magnetic field. And you could actually see, okay, this is the first direct evidence that the composition is being changed by the magnetic field. O plus either cannot get in here, or else we're restricting energetic particle source to the outside of magnetic field regions. As I said, we still have a problem being looked at. Does the main ionosphere layer actually rotate with the planet into the night? In terms of precipitation and auroral processes, the IUV spectrometer, originally we were surprised we're not expecting this. We see diffuse aurora early in emission. They're looking down. We see intense emissions coming from altitudes below 100 kilometers. And these were in the northern hemisphere, no magnetic fields. These are not the discrete auroras you see on Earth. They're not the diffuse aurora you see on Earth because they also require field lines to couple into the magnetic tail. But we have the measurements. The solar energetic electron particle, SWIA, is actually seeing up to keV electrons at the same regions where we saw the emissions. And we've had other consequences. First, we haven't been back in the northern hemisphere to see these things in a while, but every time we had a solar energetic particle event, IUV spectrometer actually saw the aurora. I have one. This puts in specific. Besides these diffuse aurora, which aren't very discrete, just recently we've had campaigns with the IUV spectrometer, and we're seeing the discrete aurora. And the Mars Express PCAM detection saw it too. Where they saw them was between, these are the cusp between the different magnetic field regions where the field lines open up in the tail, or maybe even a reconnection going on. We were seeing these with Maven. In fact, further, we were seeing another aurora, proton aurora with the IUV spectrometer, where the solar energetic particle protons are getting down and causing the effects. This is more appropriate for the magnetospheres, but this is a recent development. Remember I said these magnetic field loops we have are really mini magnetospheres, but they're big magnetospheres. They're going out to 1,000 kilometers or so. And this is evidence of one case. We found trapped the electron populations when Maven was going through a closed dipole loop. We have electron populations. We have evidence they're bouncing along the field lines. They're drifting like they do in the inner magnetosphere. And we have dispersion of the energies. As you can see, it's sort of like dropping with energy as time as it drops in altitude. These are exactly the size. I think the analogy has been given on closed field lines on the Earth. Where you get impulsive injection is if you have reconnection of the tail, you get dipolarization, you inject electrons on closed field lines, and they have this dispersive packs like this. On Mars, we're getting many of these things. We're not quite sure what the ejection mechanism is. It has to be happening at the edges, at the cusp of these things, but we haven't identified them at the present time. Another interesting thing, Mars Express saw samples of this that's becoming valuable for Maven. When a solar wind hits the extended neutral corona, you get charge exchange between essentially the superthermal solar wind electrons with these stationary corona particles, and as a result, you neutralize the solar wind H. These propagate through the magnetosphere without imposition. When they hit the atmosphere, when they hit the CO2, it's sort of like a meteor coming in. You get charge stripping on the hydrogen, or you get charge exchange with the ionosphere. You get the solar wind particles back down below. And maybe don't want to explain this, but basically, this is an example, not the greatest quality, but in the solar wind, the peak of the solar wind energy is by the dashed line. When you go inside the sheath and the inner magnetosphere, you can see the solar wind energy being degraded just as it penetrates into the magnetosphere. But as you get down to low altitudes, below 200 kilometers, you're getting particles, protons jumping up, back scattered and forward scattered at the same energy peak as the solar wind. This is an indication these are solar wind particles that didn't have to go through the intermediate region. They were neutral once they got down into the atmosphere. And what's great about this, Maven's Orbit, if you saw the orbit, it goes out into the solar wind, but it rotates sometimes, and apogee is in the tail. But we're now doing correlation. The energies of these particles are being correlated with the solar wind energies, so we're having a proxy by using these measurements at low altitudes. We get a proxy of what the solar wind's doing. But I should say Mars Express also takes solar wind observations, and we're using those. But in case we don't have MEX observations, we can use this to monitor solar wind. Reconnection. This is a case, I can't possibly go into this. This is where the magnetospheric physicists give you those 6-panel things with different multicolored energies and pitch angle distributions and magnetic fields. So I'm just showing you the type of effects we have seen. Take my word for it. You get all these details in these 2 papers. But we're seeing reconnection in the tail like you do on Earth because of the current sheet breakdown. And the observation as Maven went through, we saw ion flows into this region, and then you saw ion outflows coming towards Mars, and we see trapped electrons on here to be in the close thing. So it's like reconnection occurring in the tail. And the other one, with these draped magnetic field lines, when the solar wind is blowing by, it stretches these field lines. And if the pressure is such, it'll actually drive the opposing field lines together. So you'll have the dipole fields in the magnetic remnant regions will be stretched and pressed and inside so they break off. And there's evidence we have this with flux ropes going on too. So this is actually the draped field lines, the cusp are breaking off by reconnection. It's not the tail, but you're getting many current sheets inside these magnetospheres, and they both have an effect on escape. These are changing your particle dynamics. For escape, I'll get back to this. The main tenet of Maven is actually to escape. I didn't want to avoid it totally, but this is one orbit of Maven, and it's characterizing from static observations. It's very difficult to see, but you have the vectors of the ion motion. And what we see are 3 things. First of all, in the solar wind, well, first of all, this is the electric field of the solar wind. This is, for those who aren't into the solar wind stuff, the solar wind is made up of ionization. It's a conductor, and it's moving across the interplanetary magnetic fields. If you move a conductor across a magnetic field, you generate a voltage. This is how we get our power on the Earth. So this is where this convection electric field is coming from. It's very important because all the dynamics we're seeing of escape is being driven by the penetration of this electric field down into the ionosphere through currents and just direct acceleration of particles going on. But this one orbit, okay, we see effects of the pickup ions upstream. When the protons in the solar wind charge exchange with the corona, the neutral O, we get pickup of O+, you create O+ ions, they're standing still, and this electric field of V cross B actually accelerates them towards the planet. We have an effect as we go towards the side in the electric field direction. We are seeing escape, and I'll give an example of this. Accelerations occurring from deep in the ionosphere all the way out. And the conception right now is the major loss of atmosphere and ionosphere from Mars might be in this plume zone. We hadn't anticipated that. We thought it would be pickup or else tailward escape, just flows coming down the tail of the planet from the sheath, processes in the sheath of the planet. This is an example, a fortuitous one, static measuring the plume and what we're seeing. At low altitudes on one orbit, okay, this is a spectra, the energy, okay, versus mass, the ion mass on a vertical scale. And the O2 plus on top, this first plot, these are essentially moving at spacecraft velocities at 250 kilometers, very low energy. As we go in altitude 300 kilometers, you'll see the energy of the O2 plus, the major species in the ionosphere, beginning to shift to higher energies. 400 kilometers, you really accelerated these things, and 500 kilometers, you're out in the KeV range of these particles. We actually have an event where it's going right out the system, and we think from observations, statistical observations, this is the major process for escaping of the ionosphere, which of course, if you escape the ionosphere, you're getting rid of the atmosphere that created the ionosphere. And I just want to close with, this is an ongoing process. The purpose of Maven is first, in an empirical sense, to measure the escape at the present time, the net escape from the planet. And to get into the physics, we'd like to know how the net escape changes depending upon solar EUV, maybe the solar wind, the coronal mass ejection effects, or what other phenomena going on. The location of these magnetic anomalies have an important role as to escape. If the anomalies are facing sunward, they protect the atmosphere. You don't get escape. If they're on the leeward side, the atmosphere could be just picked up by the solar wind. But this is a work in progress. In order to calculate the fluxes coming out, we're taking a shell around a planet. Right here, I believe it's about 1,000 kilometers in this one. And we're measuring all the ions moving through that shell, and we're integrating everything. And we're dealing with, on this plot, we're just doing 10 eV up to 20 keV particles, high energy particles. Masses greater than 9 MeU, it means molecular ions or the heavy atomics. And we actually come up with an estimate of the ion loss on this. On the top side, the color coding is the outward losses. Nighttime is on the side. Most of the losses are nighttime, the blue going up. But one thing we had in mind, if you look at, there are also inbound fluxes too. If you have this shell on the day side, you tend to, all these pickup ions are moving down, so it doesn't contribute to the loss. And this is a plot showing the log of the flux, the outbound versus the inbound. On the day side, you can see all these inbound particles, outbound at night. So we subtract these from the profiles to get this. It's predominantly a loss at high latitudes and up over the night side features. Now this is exciting. We're getting losses comparable, well, it's actually repeating what Mars Express got in some ways, but we're under different conditions. These things are going to change with solar conditions, so we're going into a detailed analysis of how the sun is controlling this through its EUV radiation and solar wind impacts, and this is going beyond. But even these fluxes will just put a dimple in the escape going into the past. It's not enough to actually extrapolate into past to get rid of the amount of atmosphere we saw lost on Mars. But we're hoping, when we're looking at coronal mass ejections, some events, on localized events, we seem to get much more escape going on when we have the events. So basically, an active sun will give you more escape going on. And going back in the past, that's what we had, much more active suns billions of years ago. And one other thing to keep in mind, we're talking about ion processes. This is where the ionosphere is actually being pulled out and thrown down into the solar wind. There are other processes. Genes escape, just the hot thermal. I showed you the corona. The thermal distribution at high altitudes above the exobase, if you have enough temperature, it'll get lost. We're doing coronal observations, but we're just seeing the density distributions. We have to do analysis of actually what the energy distributions are of the coronal particles, what is escaping. Essentially, photochemical escape, this is where O2 plus and NO plus, dissociative charge exchange with electrons to give you hot nitrogen and oxygen, which could escape from the planet. Now, we can't measure these hot oxygen and nitrogen, so we have to do a lot of modeling. And intensive modeling is going on, both of the corona and also the sources down below. And the other one, which may have played a big role in the past, with energetic particles hitting the atmosphere, for example, if we have pickup ions coming in, hitting the atmosphere with very high energies, it's going to knock the CO2 or argon or other species out of the planet. This, again, we can't see the neutral processes. And it is saying that these losses may exceed the ion losses, but this is something evolving. Now, Maven's only been up there for a little over a year, so it's kind of spectacular what they've done. On Earth, it's taken 30 years or something to see some things like this in a magnetosphere and ionosphere. And I just want to close. This is, Bruce Joukowsky usually uses this as a startup, but I just want to emphasize, this is planetary. We're going to have planetary missions for quite a while, possibly because of interest like this from the public. But I'm sad, I don't think we will ever have another upper atmosphere ionosphere mission at Mars. I think Maven's going to have to do it all, and Maven has the capability of doing it. But that's where I'm at. Okay, thank you.